Hello, everybody. Welcome to ETM 507, the ETM Graduate Seminar, as well as the Technology Management Distinguished Speaker Series. This is our first event of the new year, 2023. And for those of you that are taking this as a class for credit, just a reminder on a little bit of logistics. So first of all, my name's Tim Anderson. This is the first seminar. There is already a spot for a brief speaker write-up to be posted. And please be sure to get a screen capture, image capture showing your name as the attendee to embed within the Word document or the document file as an image, as kind of confirmation showing both that you were here for the today's guest speaker, Dr. Warren Hearnes. And so without further ado, I want to introduce Dr. Warren Hearnes. I've known Dr. Hearnes since our days at Georgia Tech together back in the Industrial and Systems Engineering Department back more than a couple of years ago. Dr. Hearnes and I have been regular attendees at Informs over the many years since for the Informs, Institute for Operations Research and Management Science annual conferences, where we've run into each other over and over again over many years as we've both moved more into the area of data science and analytics. And so Dr. Hearnes has moved through a variety of positions and organizations, including time at Cardlytics, and is now the Vice President and Chief Data Scientist for Best Buy. I'm from Minnesota originally, and saw when Best Buy, the stores were even before they were Best Buy, and so at the very earliest days. And so it's a pleasure to welcome Dr. Hearnes to give us his perspectives on his career traversing the world of data science. So without further ado, please take it away, Dr. Hearnes.
Thanks, Tim. I appreciate the invitation. I'm going to go ahead and start to share my screen real quick. And let's see. I think, Tim, can you see that?
Yes, I can. It looks good.
Right, perfect. So yeah, I really appreciate the opportunity to talk to you all, and I just wanted to say thanks, and that this is going to be more of a high-level perspectives of what I've seen in the 30 or so years that I've been doing this. Kind of look at things from both a historical fashion, but also kind of relating some of the areas that I got into, like reinforcement learning, to basically everyday life. So hopefully you will get something out of this that you can apply to your everyday lives, and also some of your research. I think Tim told me that it's a pretty wide variety of backgrounds. Some engineers, some data scientists, some people that are in school, some people that are already into their careers. So I will try to come up with some examples and things that kind of relate to all of that. But certainly, Tim, if you'll let me know when there's some questions or things like that. I'm not sure if we'll leave some of those to the end, or if we will we'll answer some as we go. But I'm ready to get started. All right. So let's see. Did I get to the? There we go. So just wanted to talk a little bit about my journey over the past say 30 years. I started at Georgia Tech in the fall of '92. Can't remember if Tim was starting that year or if he was there a year or so before me. But I've always been really interested in using math to make better decisions. So some of my milestones here are that I graduated West Point, was planning for a career in the Army, did mathematics operations research there. In 1992, got out of the Army after the first Gulf War and after the Berlin Wall had fallen, and decided to come to Georgia Tech and study operations research. Now, while I was there, and we'll talk a lot more about this, I found that that PhD students got funding while master's students didn't. So I decided to go ahead and work on my PhD. And I got connected with one of the few professors at Georgia Tech at the time that had some grant money for doing machine learning research. And so we worked in the area of reinforcement learning. We'll talk about that in a little bit. Professional experience has gone all the way from the U.S. Army to my GRA days there at Georgia Tech. And while I was here at Georgia Tech, I met a girl from Atlanta. So all of my roles have been here in the Atlanta area. I love it here. First role was doing optimization and scheduling for Lucent Technologies, making fiber optic cable. Then after about 6 years of that, spent almost 8 years at UPS doing some machine learning, pricing optimization, and regular optimization for UPS. Spent about a year at the Home Depot standing up a marketing sciences team. Then got a chance to go over to a startup that I was there for 10 years. We did eventually take it public in 2018. And then earlier, well, I guess we're in January 23 now. In January 2022, I got a chance to jump over to Best Buy as their chief data scientist. So that's a little bit about my background there. So just to give you an idea, I've been through the entire spectrum of a researcher in academia to an individual contributor, then worked my way up into management, and now as an executive. But you know, it's all about using some type of math, whether it's statistics, whether it's machine learning, optimization, simulation, you name it. The focus in industry, at least for the companies that I've been in, is to figure out how we can use the data that we've collected and the information that we know about either our customers or our processes, and create models or use machine learning to solve some very important business problems. And that's really where I have gotten my excitement throughout my career. So here's a couple of areas that I would like to touch on today. That AI has a long, rich history, and that there are some parallels between reinforcement learning and real life. We're gonna get into this a little bit more, but I had a few more of these that I was going to talk about, but I'd rather dive into these and go a little bit deeper than hit on a couple of them. Hit 3 or 4 shallow. So this is where we're going to look at. And I'll say this, all of these photos, I guess these images, are all from OpenAI DALL-E. So I know that a lot of you are hearing about ChatGPT or DALL-E, which is the generative AI for taking a text prompt and turning it into something. And I like it so much in terms of creating these pictures for some of my presentations that I've actually paid for extra tokens to do this. So this was an example of one where I said we were doing something with Python, and I said I want a Python and a computer together, and actually looks pretty good. So you'll see that almost all of these photos are generative AI, which is a whole area we can talk about at the end if you would like to. All right, so I've been around long enough that I have seen what we do for industry be called many, many different things. Statistics, operations research, all the way down the line, industrial engineering, through data science, through machine learning, evolutionary computation, artificial intelligence. But regardless of what we're calling it, a lot of these are related, and maybe you've seen some of the debates on different forums about, is machine learning part of statistics, or is analytics part of data science, or data science part of analytics? There's a lot of interesting debates about what each one of these mean. I take the view the more nuanced view of it doesn't really matter what we call it, as long as in industry we are using the right methods and the right data to solve these problems. It doesn't matter whether somebody calls themselves a statistician, or somebody is a data scientist or an ML scientist, or even I've heard now we've got some AI scientists and AI engineers. So, this is an area where there's a lot of names, but it's really a lot of the same things. Hopefully that makes sense. And I can't see if there's any questions, and I can't see the chat. So if there is, Tim, just let me know. So I wanted to start off talking about some of the history. So in January, there was a paper published called Steps Towards Artificial Intelligence. And in this paper, we had, the author talked a lot about 5 different areas that were problem areas for artificial intelligence. And it included these 5 areas: search, pattern recognition, learning systems, problem solving and planning, and induction. And if we were there, I would be asking for a show of hands on, who is familiar with at least a few of these, like the gradient descent algorithm, or reinforcement learning, or the credit assignment problem in learning systems, or breaking down problems, larger problems, into smaller solvable ones. These are some really important areas. So, I know that a lot of you are seeing some of the work that either you're doing for your industry or some of your classes in these. Now, what I want to say is that wasn't January of this year. That wasn't this month. That was January 1961. We're talking 62 years ago. Marvin Minsky wrote this paper and outlined. It's a great paper. Look it up on Google. But the point is not that I don't want to say that we're just doing the same things. What I want to point out is that we are building on things that have been around for a long time. We're standing on the shoulders of giants, and we take what they've learned and we enhance it, or we add to it, or we create something new from it. So I just wanted to, this is something that I talked to a lot of the people that are early on in either their academic or their industry career, and make sure that they've looked at some of the seminal papers in the area. So I think what we'll do next is go into some of the milestones in a few of the areas of machine learning, just to give you an idea of the length of time that we've been looking at these problems, and also to say that there sometimes can be years and years between one development and another development. If we're getting a lot of excitement, like right now around ChatGPT, there was a lot of work that went into that. It's not something that happened overnight. So, I think this is the next few minutes will kind of give you a flavor of how long people have been thinking about this, and go from there. So, for neural networks, people came up with a computational model many years ago, and I had to move so 1943, I had the window in front of the way. McCulloch and Pitts came up with the computational model. Then Hebbian learning, the idea that if 2 neurons fire together, they should wire together, or make in that sense, make a stronger connection. That idea of learning was 1948. And then in the 2-layer perceptron, it's 10 years later after that they said, hey, we'll take not just this idea that there's a single perceptron, but let's make 2 layers of perceptrons. The ideas for backpropagation, there's a lot of work around that, but Paul Werbos came up with, in either 1974 or 1975, I went ahead and put 1975 here. He came up with the ideas and the mathematics for backpropagation to use, and said you could use it in a neural network. But it wasn't until 10 to 12 years later that it was actually applied to neural networks. So, I thought this was interesting to see the ideas and their flow. And sometimes it's not this linear, hey, everything's going and we're going to make constant progress. It's more of the start, stop, try something, fail, try something, succeed, which is an entire theme that we're going to go through in the rest of this talk. Logistic regression. So in the 1830s, and I'm not sure how to pronounce his name, so I won't try, but they used it for population growth. And then it was almost 100 years later that Lowell Reed said, hey, I think we can use this for statistical binary classification. And then it was another 38, 40 years later that it was formalized and became such a good method for estimating the probability of two possible values. Decision trees, same thing. Regression trees came out first. Almost 10 years later, classification trees. And then guess what? Classification and regression trees was another 12 years after that. So, same idea of, hey, this is not something that is happening over and over, or excuse me, quickly. It is happening. These ideas are being proposed, tested, and then they may fall silent for a little while, and then somebody else takes it up. Support vector machines, 1963 for the linear classifier, and then in the early 90s for a nonlinear classifier. And then we get into the area which was my PhD research, which is reinforcement learning. So reinforcement learning, we'll dive into this. It's based on a lot of the dynamic programming concepts that Richard Bellman came up with in the 1950s and 1960s. So on my bookshelf back there, I've got some of the early work for Bellman from the Rand Corporation, because my advisor at Georgia Tech was Richard Bellman's first PhD student. So just about everything that we did had to tie back into dynamic programming, and reinforcement learning was a great way of doing that. Minsky, the same Minsky from the paper from 1961, Minsky, Farley, and Clark had something called trial and error learning, which was, it's very similar to reinforcement learning, but it's less about maximizing a reward, and it's more about trying to generalize some of the mistakes that you made. There was a 1961 example about how a reinforcement learning model could play and win at tic-tac-toe, or at least not lose at tic-tac-toe. So think about how far we've come in that respect. That an example of playing tic-tac-toe is revolutionary versus what we've got reinforcement learning doing today. And then temporal difference learning, Q learning, are two different ways of estimating the value of being in a specific state and taking an action. Whoops, I hit the wrong button. And then the latest, the major milestone is the use of deep learning in reinforcement learning, and DeepMind started that around 2013. So again, I'm not getting, it's hard to tell how people are if we've got questions or anything like that, since this is a purely virtual and I don't hear anything, but please let me know if there are questions. So I think, we have a lot of a lot of machine learning that we use is based on biological roots. And I think this is something, as you get into, if you're going into a data science career, then I think this is an area where if you can look at the way that certain natural processes, whether it be them animals or groups of animals or people or children, learn, then I think this is an area where you can start to understand the basis for a number of the algorithms that we have developed. For instance, the neural networks, we talked about this a little bit in detail at the beginning, but it's the idea that the human brain can do so many amazing things, and it's a collection of, I don't know the number, but a huge amount of neurons that are all have different links, and the image recognition, the understanding, some of the things that we can do as humans are simply amazing, and not just humans, but also animals. I think this is an area where in industry, we're still at the point where the best neural network that we have available is our own brains. And there's going to be still most of the machine learning and AI that we have is going to be human in the loop machine learning or human in the loop AI that helps us make better decisions. Now, maybe at the end of my career, or maybe sometime in your career, we may get to a point where the AI that we have created can do some of these things better than human brain. But frankly, we're not there yet for a lot of this. Another area that was big in the 80s and 90s was genetic algorithms, and it was inspired by the idea that evolution, two genes, two parents coming together, generate an offspring, and that offspring should, if it can compete better in the environment, should survive longer and therefore have a higher probability of finding a mate. And the interesting things about genetic algorithms are it's a great biological process, but how do we make sure that the DNA that is in, how do you encode the DNA of your problem? Swarm intelligence is a really interesting area that got a lot of traction a number of years ago. And that was the idea that groups of animals, so you can think of it as, there's one called ant colony optimization. And then I think there's one that's based on how bees do things. But, it's the swarm intelligence. It's the idea that there are agents within the system that each have their own either rules or their own objectives, and the system itself creates something that the entire society or the entire swarm improves. And then lastly, reinforcement learning is inspired by the ability for animals or children or other systems to learn from their experiences and adjust their behavior in order to maximize or optimize for rewards.
So a quick question from the chat was on reinforcement learning. Is positive or negative reinforcement learning typically better?
So that's a great question. Because I will say that there's a saying by Mark, it is attributed to Mark Twain. And we'll get into whether this is both negative reinforcement and the credit assignment problem that we'll talk about in a second. But Mark Twain once said that a cat that sat on a hot stove will never again sit on a hot stove. So that's the negative reinforcement. Or on a cold stove either, meaning it didn't know how to take, didn't know whether it was the hot or it was the stove, and it's just not going to do anything. I had some, now this was back 20 years ago, I had some interesting conversations that some other researchers disagreed with, but my contention is that negative reinforcement is a lot more beneficial at the beginning, and then because it kind of sets the boundaries for it. But then once you're getting away from those negative boundaries, then you get to the positive reinforcement. That's just my intuition on this. I don't have a way to prove that, but you're telling the computer you get a +1 if you get to a goal state, you get a -1 if you get to a failure state, and anything in the middle, it's all about what we'll talk about in a little bit of generalizing the learning or the credit assignment problem. But that's a great question. I don't have the answer to that, but it's my contention that negative reinforcement earlier on in the problem or in the modeling is more beneficial. Now,
that part about swarm intelligence reminded me of Dr. Craig Tovey from Georgia Tech. He was doing a lot of work on that even 30 years ago. Yeah, so and that's not to say, and I guess this is not to say, hey, it was done 30 years ago, and therefore it's not valuable now, because you're seeing that neural networks were 60 years ago for some of these things. Reinforcement learning 60 years ago. Some of these ideas, they grab hold right when they come out, and other ideas just take a little bit longer to either grab hold, or maybe it's in the case of, say, machine learning, some of these ideas worked well, but we didn't either have the computing power or the massive amounts of data that you really needed. I'll say it was a little hard for me to convince some of the tenured professors at Georgia Tech in the 90s that a system that learned, a model-free system that learned and improved itself over time, but you couldn't prove that it was optimal, was still a worthy of research, because at that time it was, you've got to prove it's optimal. And if you're going to prove it's optimal, you got to have a model. And I said, well, there's so many things in this world we don't actually have a good model for. So that's what we're looking at. How are we doing on time? So we've got doing great.
All right, so here's where I'm getting a little meta, not the company, but meta as in higher up, about all of this. I became really interested in reinforcement learning in the 90s because of its, as I have in the title, because of its connection to real life. It made so much sense to me. And if I was going to spend years researching something, I wanted to be excited about it. So the basic components of reinforcement learning is that you have an agent. It's a decision maker. That can be, I had a dog that I was teaching a lot of tricks, and kind of taking some of the information, or some of the learnings that I had from teaching a dog a trick, to seeing how we could teach a computer a trick. And so you've got the agent, you've got the environment that it's in, you've got its current state of the world, and that's the current condition of the environment. And you can argue whether that's the actual condition of the environment, or is that the perceived condition of the environment by the system. That's when you are in the environment in a specific perceived state, then you've got to make a decision. Almost everything that we do in life is making decisions. So you've got to figure out, I'm here, I need to make a decision. To help me make that decision, I've got to have some prediction of what's going to happen in the future if I take this. So that's the transition function. So it's like, it's easy when you're in a car. You turn if you're steering the car and you turn the steering wheel to the right, you're going to go to the right. But if you're in a system that has a lot of uncertainty, then it's more about trying to make the best decision and not worrying as much about the outcome. because the transition function and the reward and doing this over and over will implicitly learn that uncertainty. The reward is the value that you get from its actions, and it can be the actual explicit reward at the end, the positive and negative reinforcement. Whereas in a lot of the system, you may not get any explicit reward, but you have learned to these implicit rewards for going from one state to the other, such as you've got students that are working towards a degree. So they know that the more credits that they have successfully completed, the closer they get to that. They don't get the degree. They don't get that true reward for the degree until they have the right qualifications. But each one of these implicit rewards, other than the fact that Tim is teaching them all of these wonderful things in the class, and that's a whole reward system to itself. But you've each one of your students is saying, hey, I'm now a sophomore, or I'm a junior, or now I'm a senior, or working on your PhD. Policies and value functions, policy is just your strategy. And so some of these policies, most of these policies are not optimal. There's going to be one or more optimal policies based on the system that you define. The key is to get closer and closer to that optimal policy. And as I said, the parallels to real life is what kept me interested, because almost everything that we do is a sequential decision-making problem, whether that's personal life, whether that's work life. It's wonderful that we have integer programming that can solve. You can take some inputs. When I was at Lucent Technologies and I was managing the shop floor, I would take the orders that came in, I would know what inventory we had, and I would create the optimal schedule. But that was the optimal schedule for that day. And then the next day I had to run it again for another optimal schedule and another optimal schedule. Because if I tried to run the optimal schedule for the entire week, there's a lot of uncertainty in there of breakdowns on machines and things like that. And after a little while, that uncertainty makes my original optimal schedule pretty suboptimal. So it really is, you've got some information, you make some predictions, you take an action, you get a result, and now you're making another set of observations. So there's a few things that I wanted to hit real quick on some of the areas of not just reinforcement learning, but generally machine learning as a whole. The credit assignment problem. We kind of talked about that a little bit with that saying by Mark Twain. What caused the negative reinforcement for the cat? Was it the cat sat on a hot stove? So you've got something that's hot and something that's a stove, and the cat, it's going to rarely ever try for either one of those again. But the credit assignment problem is one of the main challenges when you're in a fairly complex system. We think of the hot stove as not being a very complex system, but as we're doing reinforcement learning, or as we're doing machine learning in a lot of the complex systems that we see either in industry or in robotics, then that getting to that final state is not only delayed, but you had so many things that went on during that. Is how do you tease out what were the things that were the right ones to give the assignment to? It's not it's similar in analogy to feature engineering or principal components, things like that. It's trying to figure out what is the most important thing, but it is an integral part of a machine learning algorithm. Then the idea is, how do we generalize that? I'm sitting in a particular state in the system, and I take an action and I learn something. Does it mean that I can generalize that to something else. And you can either discretize a continuous state space, or as what we were doing in the 90s, we were using fuzzy set theory. Now we've got deep learning, radial basis functions. The idea is that we don't have enough time to try every single state. The idea is that if I learn something, then how do I generalize that so that I can not start from zero in the next state? And then exploration versus exploitation. So another basic problem in all learning algorithms is, how do we know when to explore new things and improve our knowledge, because we can't prove that what we're doing is optimal, versus exploit the knowledge that we have. It's a real life example. Let's go back to most of you all are in college. You know, the idea is, let's explore, when you're a freshman, let's explore a lot of different types of studies. Maybe I want to be a mathematician. Maybe I want to study literature, or maybe I want to do some of these things. You're exploring different things. And then you get to the point, so it's more of a breadth first search. And then you get to a point where you say, hey, I think I know. I'm gonna be a management major, and I'm gonna start taking a lot of these classes, and I'm gonna kind of exploit that, and I'm gonna learn some things. But every once in a while, you might either take a different class, or you might get a year or two into this, or when you're in your career, you might get a few years into something. I've done data science my whole career, but I've done it in a factory setting. I've done it in a logistics setting. I've done it in a retail/marketing setting. I've done it in an actual advertising fintech setting, and now I'm doing it in consumer electronics. We're doing all of it. We're doing supply chain. We're doing marketing. We're doing store operations. So there's different areas. So the idea is that, hey, when do we focus in on something and kind of exploit the knowledge that we have, versus also saying maybe that's not the only thing out there. So so here's an example. Chat GPT is so huge right now. This is an example of explore versus exploit. Let's explore what we can do with some of these GPT models, some of the large language models that are the pre-trained transformers. But what they are doing fundamentally is just learning the sequence of words. You give it some tokens, and it has read just about every document that has ever been written that's out there on the internet, and it writes some beautiful, mostly correct, but not always correct, but it's almost always confident, even when it's not correct, and it looks great. So we are exploiting that. But this came out from the MIT Technology Review right before, a month or two before ChatGPT came out. But MIT is saying, hey, we might run out of data to train these large language models. So fundamentally, the question becomes, as we tie this back into machine learning having biological roots, I have two kids, and they're in college now. Well, one just graduated and one's still in college. I didn't teach them by telling them to read every single document in the world. I taught them with, the teachers taught them with let's say they've read 1,000 books in their life, and they read some things on the web and stuff like that. But fundamentally, we have a great approach right now with large language models. They can do some really amazing things. But when we start to see that, are we going to run out of data? Then fundamentally, I think there's a better way of doing it. I don't know that way. but maybe somebody on the call is going to be working in some NLP that does this. But and there's a lot of interesting research in this area. So I think this is, I'll say that I think this is more of an attention grabbing headline that MIT put out, but it does put it into perspective about is what we're doing fundamentally rooted in a biological process. When you are thinking of something, are you trying to just guess the next word you're going to say? No, you are thinking about a concept, and then how you will explain that concept, and then the words come. So yeah, I just wanted to put that out there as an example. I know we're starting to hit up on time, but a couple of parting thoughts is that my background, both in the Army, in industry, and as a reinforcement learning researcher, and now as a data science executive, is you've heard the saying, failure is not an option. Well, failure, I think, not only is an option, but it's required for success. What I say is that quitting is not. So if you're putting yourself out there, and doing something and stretching, you're going to fail at some things, but you are learning from that, and that's the key. Be ready for every opportunity, and then also, one of the things that I've always liked to have is the idea that don't put things off. It's a year from now, you may wish you have started today. It's similar to I think it's a Chinese proverb of, when's the best day to plant a tree? It was either 30 years ago or today. Those are so that's what I wanted to get up to. I did have one other slide that we definitely don't have to have time for. It's kind of like my journey, but I wanted to just summarize what I call the life lessons from reinforcement learning, which is find your motivation, find that goal, find what is that positive reinforcement. And then we talked about the value that each state is in, and just let you know that as a manager, an executive, or anything that you're doing, you are always earning a reputation. So try to maximize that value function. And then feedback is super important. We're not going to learn if we don't have feedback. And then lastly, you've got to explore, fail, learn, succeed, and repeat throughout your whole life. With that, I will open up to questions. I think we're right on the 45-minute mark. So.
Yep. So we've got about 10 minutes. And so if one question I had is, you did a great job going from being an algorithms person and a kind of a hardcore methodology person to now being a business executive in the C-suite. So
yeah, well, thanks. If you're asking, that sort of happens. For me, it was a gradual progression. And some people will say, so for 6 years, I was for Informs, you talked about it earlier, Tim, I was the chair of the Career Center. So I moderated a lot of panels. And if you're not a member of Informs, please do it. I'm now on the board, so I want to make sure that we are successful. And it's a great organization. But that said, I think, you will know when you are ready in industry. At least this is how it worked for me. If I was an individual contributor and I was learning things and doing things, then I felt like, yeah, that's where I need to be. But then you start to watch what your manager or your executive is doing, and you're learning from them at all times. Most of these things are hopefully really good, positive things that you're learning from them, but you might be learning how you don't want to be treated. But when you start getting to the point where you feel like you can make as good of decisions or better decisions than they are making, then yeah, I'm ready for the next challenge. Because And that's how it was for me. Went from individual contributor, and then many years in the management ranks, and then the last, say, started at Cardlytics as a director, but then moved up into the VP, SVP, and then as an officer at Best Buy. So it's and I'll say one other thing on that is that, especially for those of you that are working on PhDs, it is a uncomfortable feeling going from being somebody that knows the most or almost the most, in the company about something, to being at the executive level and knowing that just about everybody on your team is more familiar with the problem and more familiar with how they're solving it than you are, because you're spending a lot of your time in meetings doing budgeting, doing resource planning, doing strategy. But it's where I have gravitated to. But you don't always have to do that. You can be an individual contributor and move up into the principal roles throughout your life.
Are there lessons learned from your experience in reinforcement learning and how you manage teams or work as an executive? And especially with your culture for your organizations and
so I think it does get to this lesson number 3 right here. I think there's a book called right there, Kim Scott, Radical Candor. It's talking about feedback, and many of us that are in the fields that lead into engineering or data science are more introverted, and we may not want to give that constructive feedback all the time, but I do think that getting and giving that feedback is super important, and then giving the word now is psychological safety, but it's the idea that you're giving your team the idea that they can explore something and fail. They don't have to succeed at every single thing that they're doing. And especially in a data science group, we're not pushing the envelope if every single project that we try, we succeed. We have a discovery process that says, hey, do we have the data to solve this problem? Let's go take a look at it. Maybe we have the data, but we can't solve it. So I think those two things, the feedback and the psychological safety, go back into the way reinforcement learning assigns the credit and then allows failure.
So let's take one last question from the chat. I really appreciate your spending what is now after 7 o'clock Atlanta time. So thank you on a Friday night. In the chat, there was a question. In the industry, what's the role of statistics compared to AI? Under which circumstances does the industry use statistics?
So that's a great question that could take. Number one, there's different ideas on this, and it depends on your industry. Let's focus on the ones that I've been in. I haven't worked for Google or Meta and some of the other ones that are really into a lot of the machine learning as the primary thing that they're doing. That said, statistics is still used widely in our marketing measurement. It's used in a number of areas in a retailer. It's used in a number of areas in a logistics company. So where you're going to get a lot of, I would say, if you're going to discuss this with people, there's the idea that just get a definition of where machine learning ends and where statistics begin. Because when I was at Georgia Tech, machine learning would have only been the subset of algorithms that would have been like neural networks, to where they get better over time. But nowadays, machine learning it includes logistic regression. It includes just about any type of algorithm that creates an answer from data. So I guess one of the last things I'll say on this is that I don't fight the semantics anymore. I say as a data science executive, it's the improv rule of yes and, where you agree and you say and you agree with what somebody says, and this is the next thing. If somebody says integer programming is data science, and I'm like, yes, and that's why it should be all together in one team rather than doing it off to the side. When same with statistics, I've got a number of people that are classically trained statisticians on my data science team, and we call them data scientists. And most of what they are doing is causality and a lot of the things that you worked on in a statistics framework, but now there might be some new interesting ways of doing that with either neural networks or some other type of package that's out there.
Yep, great. Well, and it's consistent with we've started a business intelligence and analytics graduate certificate program at PSU that I helped co-found, and a class that I teach, operations research, I use as kind of a secret way of teaching R along the way, and tools. The data science pipeline is a way of getting started with optimization, and so that people have a rich toolbox with which they can then use thousands of other tools to build off of.
I agree. It's there's a lot of things that you can do with, I want my team to be happy, just as happy using deep learning, which I'll say for most companies, you're not using deep learning on most of your problems. So if you're thinking that you're going to go out there and that's what you're going to be working on, they can be solved by something that's out of my undergraduate statistics textbook. So you need to be able to say, I'm going to use the tool I need to solve the problem.
Yep. Great. Well, once again, thank you very much. This was a great talk. I appreciate it. And I hope to see you probably at the Informs National Conference in October.